In this presentation, we will go over electrochemistry and its connection to Gibbs energy. For this lesson, we'll explain the differences between potential, Gibbs energy change, and equilibrium constants. We'll perform calculations involving relationships between cell potentials, Gibbs energy changes, and equilibrium. So first things first, what are these relationships? Gibbs energy can be thought of as electrical work. So moving electrons along. So in physics, that is defined as negative N Fe naught cell. So N is number of moles of electrons transferred. F is Faraday's constant, which is 9.649 times 10 to the fourth coulombs per mole. And E standard cell is straightforward. If you remember, we had defined delta G as minus RT ln K in the previous chapter. If we take that, actually, that wasn't the previous chapter, but nonetheless, it is still a relationship we have. And we set minus RT ln K equal to the other G naught equation that we have. We get minus RT natural log of K is equal to negative NFE cell, or E naught cell. All right, so if we isolate E naught cell, we get RT over NF natural log of K. And for the record, if we were doing a non-standard cell and it wasn't E standard cell, we would still have the same equation. We just wouldn't put the naught in there above the E. Okay. Okay, so we have a relationship between our delta G, our E naught cell, and our K. We've just defined all these equations to get back and forth between the things. So if K is greater than 1, if you plug it into the delta G equals negative RT ln K, then we find that delta G is less than 0, because natural log of a positive number will be positive. We multiply that times negative, we get a negative number. Therefore, when we plug that into the delta G equals negative NFE cell, we get an E cell greater than 0. So if K is greater than 1, we have a spontaneous change, and our products are more abundant at equilibrium. If K is less than 1, when we plug it in, we'll get a positive number for delta G, and we will get a negative number for E cell. That would be non-spontaneous. The reactants are more abundant at equilibrium, meaning we're going to push back towards the other direction. All right. And if we're at 1 for K, then delta G is 0, because delta G is 0 at equilibrium and K is 1 at equilibrium. And E cell will also be equal to 0. So at equilibrium, reactants and products are in equal abundance. We already knew that, but now we have another way of knowing that. Use Appendix L to calculate the standard cell potential, equilibrium constant, and Gibbs energy for the following reaction at 25 degrees Celsius. Comment on the spontaneity and composition of equilibrium. So we have an equation with copper and gallium which moves 3 electrons. Where do I get that? I get that from the fact that gallium goes from 0 to 3+. So we must have moved 3 electrons to make that work. Just look at the oxidative state. We know that copper then is the cathode, gallium is the anode, because cathode reduction, anode oxidation. And we're going to use our E cell is equal to E cathode minus E anode equation in order to solve for our E naught cell. So we get 1.070 volts of electricity. Now, we're going to plug that in to our E cell equals RT over NF ln K and solve for K. When we do that, we make sure that we use 8.314 for R, because we're dealing in energy, which should be in joules. We use temperature in Kelvin, because we always use Kelvin for anything thermodynamic. And Faraday's constant is what it is. Okay, after we evaluate that, we end up with something where we have the natural log of K equal to some value. In order to get rid of the natural log, you take e to both sides, and we eventually find that K is equal to 1.94 times 10 to the 54th. There is another way to do this problem. It will be given in the same equation that you'd see on the ACS exam in the equation bank. So I'm going to derive that equation in the next slide and then use it to show the difference between the two. Okay, so let's talk about the book. In example 17.6, they do this. They say E cell, E naught cell is equal to 0.0592 volts per N times the log of K, log log. And you may be thinking to yourself, how did they get there? How did they get there? We're going to get there from A to B. Okay, so if we start with our E naught cell is equal to RT over NF natural log of K, when you evaluate that, you put in your R, you put in your T, you put in your F, you get 0.0257 joules per coulomb times N times natural log of K is equal to E naught cell. Okay, note, we're still in natural log. So if you remember, our log rules say that if we want to change the base, log base B of A is equal to log base D of A over log base D of B. Okay, so in this case, we're going from log base E of A to log base 10 of A. So we go ahead and do that. Okay, log base 10 of E is an actual number. So we're going to go ahead and plug that in. And what you get is 0.0592 volts per N log of K, which is what they have in the book. All right, we have the same initial information as before, but we're going to be plugging our values into the alternative E cell equation instead. So we do that. And when we solve for K this time, we're going to do 10 raised to both sides because we now have log base 10. And when you do that, you get 1.67 times 10 to the 54th, which is actually fairly similar to the 1.94 times 10 to the 54th. They're the same order of magnitude, but they are distinctly different numbers. Use the formula that we just used when you use it because it's going to be on the ACS exam that way, and you should get used to using it that way. All right, we're going to calculate delta G to finish this problem off because that's the thing we haven't done yet. So we're going to use that delta G is equal to negative NF E cell, where F is Faraday's constant and N is the number of electrons we transfer, and that is 3. So we're going to plug those numbers in, and when we evaluate that, we get negative 3.097 times 10 to the 5th joules. So our delta G is negative, which is spontaneous. This is a spontaneous reaction, and the composition is going to be more toward the product side. All right, so let's summarize what we learned here. We have delta G being equal to negative moles of electrons transferred times Faraday's constant times E naught cell. We have delta G being equal to negative RT natural log of K, where K is the equilibrium constant, and T is temperature in Kelvin, and R, as usual, is going to be an 8.314 joules per Kelvin mole for this type of application. We have that E naught cell is equal to RT over NF, where F is Faraday's constant, natural log of K, which is also equal to 0.0592 volts per moles of electrons times log of K. And we know that when K is greater than 1, delta G will be spontaneous, and E cell will be greater than 0. Products are more abundant. If K is less than 1, then delta G is positive, which is non-spontaneous. The E cell is the opposite of that. It'll be negative. And we'll know that it's non-spontaneous reactants more abundant. Finally, if we're equal to 1, we're at equilibrium. And so our E cell is 0, our G cell is 0, and products and reactants are in equal or proportional abundance.